So this one strategy for figuring out what the truth table of this is was to plug in a value for P, plug in a value for Q, and see what you get. And that's what we just did. We just did two examples. We plugged in both of them true. We plugged in P true, Q false, right? A different way to evaluate a complex compound proposition is to try to do some algebra with it, as it were, some logical reductions. So let's try that strategy. All right, so if P then Q and if Q then P. So if P then Q is logically equivalent to not P or Q, right? Not takes higher precedence than the conjunction and disjunction. So this is not P or Q. It's not the same as not P or Q. That's a different thing. The not happens first. Okay. And what? Not Q or P. Yes?
For the ors in this, does that mean that it's only P or only Q, or it can also be both?
No. So remember, the truth table for or is P, Q, P or Q. Okay, this is the truth table. So it's true if either of them is true or both. There's an exclusive or operation that comes up in computer science and some things a lot, but it's not. Yeah, this or, as long as one of them is true, then or is true. Sort of defined by this truth table. One way to think of or, if you think of true as being equal to 1 and false as being equal to 0, then or is like the maximum. Okay, so then sort of what's, the maximum of two things that are either 0 or 1 is 1 if either of them is 1 or both. And if they're both 0, then the maximum is 0. Okay, and can be viewed as multiplication in this context. A and B is true if you represent true by 1 and false by 0, and you multiply the things together, the product is 1. Right? So if either of them is 0, the product's going to be 0. If both of them are 0, the product's going to be 0. The product's only going to be 1 if they're both 1. Okay, so and is like multiplication, or is like taking the max.